they are doing a lot recently. So actually in Ilmenau, they also connect the family homes now to fiber optics. So in 1, 2, 3 years, we will all have like really high bitrate internet connections. But now they use DSL with like 16 megabits, so in this order.
Currently, there is quite fluctuation. Sometimes it happens, there is fluctuation in net connectivity. So,
Yes, I always think in the afternoon it gets more difficult when all the young people and all the ones who stay at home start to watch Netflix. Okay, so let's see. 2 minutes to go. But actually, the universities in Germany are connected really well. So there's a fiber optic system connecting the universities. So we usually have huge data rates at the universities, and also the dormitories on the campus where the students live have usually really high bitrate internet connections. Okay, but this just as some remark. It starts to get more difficult where the companies don't make so much business. If you come to the more rural areas and the villages in the Thuringian forest. But Ilmenau, like with around 30,000 people, is not really a village. It's more like a small city, and the infrastructure is quite well here. Okay. But enough remarks. We want to study some more theory. So welcome to another lecture of information theory and coding. And as usual, we start with the repetition of what we did last time. So let me again remind you on the exam for the students in Kazan on January 24th. And we will have to see how much material we can treat until then. Okay, then we basically continued with some additional information on this coset factorization, on this syndrome decoding. We have seen that we can group the error patterns which will result in the same syndrome into this so-called coset M mu, so containing all error patterns with syndrome S mu. And we thought about an efficient way how to determine all the members of this coset M mu. And therefore we thought about, well, what's happened if we consider two members from a coset M mu. Of course, both will result in the syndrome S mu. So they are equal. E times H transpose must be equal then to E prime times H transpose. This simplified somehow further, so brought to one side and factored out the H transpose. So this means E minus E prime times H transpose is 0. This means the difference between these two error patterns in one coset must be a valid code word. So this we just wrote here. So the difference needs to be a valid code word because then the syndrome will be 0. Or the other way around, I get one member from this coset M mu if I know any member and I add a valid code word. And this a bit more generalized. I can get all members from this coset M mu if I know one member from this coset and I add all possible code words. So this is basically the easy way how to get this whole coset table. And yes, I actually wrote this once more here. So if we, in the first row of this coset table, we have the error patterns resulting in the syndrome 0. This actually also corresponds to the set of the valid code words, gamma. And we know if I know one member from this coset, for example, resulting in the syndrome 001. If I add to this one member all valid code words, I will get this coset corresponding to this syndrome. So I just need to find one member of the coset. This is what we did here. So if I use y being 001, I calculate the syndrome. And we should be careful here not to mix it up. Of course, this y001 could result from a 0000, which was transmitted, and an error pattern being 0001. So you can also consider this here as error pattern. Which will result in a 001. And we get the other members by adding the valid code words. We have them here in orange. So I get this member by adding the error pattern with this valid code word. So the modulo 2 sum is exactly this one, and so on. So simply by adding the valid ones, we get the members of this coset. And you could verify it if you multiply any of these error patterns with H transpose, the outcome will be 001. So this actually really works, as we have shown before. And we can do it in the same way for the other cosets. We just need always one member of this coset. And there it would be smart to use the error patterns containing only a single one to identify members of this several cosets. So this is why I started here with this one, calculating the syndrome. We found out the syndrome is 010, so I know one member and get the other ones again by adding it with the valid code words. So the 00010 added with this orange one up here will be this guy, and so on. So this makes things a little bit easier to determine this coset table. We don't need to calculate all possible combinations of error patterns, which syndromes they will result in. We just always need one member from the coset. Okay, then we actually came to a task from the exam. So there I also provided you a generator matrix for a specific code with some general questions like encoding one sequence, very easy. You just need this vector matrix product. Then we were asking for the parity check matrix. We just need to know how to build this parity check matrix, also very easy. Then task C, we asked to complete this coset table. So we had some missing entries here, but the hint or the idea that you needed there is that, of course, with the syndrome 0, we have the error patterns which are equivalent to the valid code words. So this means the missing entries here must be valid code words. And we should know that all the rows of G are valid code words, as we have shown before. So, and if you look at it, you see exactly the missing ones here are the rows of G. We have here 3 more valid code words. And we know for linear block codes, as we describe them by generator matrices, of course, also the all 0 sequence must be a valid code word. So this is the 4th one missing. Then we needed to select the coset leaders. There we select the error patterns with the lowest number of ones, because those are the ones to appear most likely. It's more likely that only 1 bit is wrong as if 4 bits were wrong. So this is why if we observe the syndrome 001, then most likely just the last bit was wrong. It could also be that the last 4 bits were wrong, but this is more unlikely. So we forget about this case. We are interested in the most likely transmitted sequence. So at the end, we will actually only need the coset leaders. and the corresponding syndromes. We will store this in our receiver, and for any received sequence, we calculate the syndrome, look up the most likely error pattern, so the coset leader, and if we know this coset leader, we can use it to correct our received sequence, which we also did here in task B. Correcting it just by adding the coset leader, which will make the entry where we have a 1 in the coset leader, it will flip the corresponding bit in the received sequence and thereby correcting it. Okay, so then we started with the low density parity check codes, just briefly in the last lecture with some general remarks like when they have been discovered and what's the problem with it, the high computational complexity or the memory demand. But those problems nowadays are solved. So this is why we see more and more applications where these LDPC codes are used. And we will get to know why they work quite good and what's the benefit of this LDPC codes. As example for illustration, I typically use also here the 7,4 Hamming code, which we know already. Obviously, as we will also see later on, this is not a very good code to treat it as LDPC code. So for the LDPC codes, we typically want large parity check matrices with only few non-zero entries. So a good parity check code might have a parity check matrix of size 100 by 1000 or something like this, with just few 1 entries. But we will see what is bad about this many 1 entries. But for illustration and for understanding, it's fine to use here the 7,4 Hamming code to explain the principles, how this works. And actually, I want to start again here today by telling you what about this parity check matrix and the relationship to the Tanner graph. This Tanner graph just being a graphic illustration of this parity check matrix. So let's start here today if there are no questions so far.
This parity check matrix, sir, is means a random example which you have taken.
It's actually the example from the 7,4 Hamming code. If you look at the generator matrix from the 7,4 Hamming code, I think we also had it. Yeah, we had it a while ago already. But this is actually the parity check matrix resulting from the generator matrix of the Hamming code in the way you see it up here. You see, if we know a generator matrix looking like this, we can get the parity check matrix like this. We just need the parity matrix transpose followed by the identity matrix. And if we do this for the 7,4 Hamming code, we will get this parity check matrix. But it's a good question, and this is also one point that I want to explain some more today. So again, parity check matrix. Maybe let's write it once more as you asked for it. It's P transpose or minus P transpose if we have non-binary modulation schemes, followed by the identity matrix, where we also know the generator matrix. We get it from an identity matrix here for a systematic code, followed by this parity matrix. For our example, and actually I want to write down H transpose, leave some space in front. I want to write some more stuff here. So we need H transpose from back here. 1, 1. Okay, so I think I got it. So we have the 1, 1, 1, 0. Then here actually followed by an identity matrix. and the 0, 1, 1, 1. And the last one, I just briefly need to look it up. Sorry, so it's the 1, 1, 0, 1. So this is H transpose of the parity check matrix. And try to remember our diagram or our drawing where we explained the relationship between the generator matrix and the parity check matrix. So just recall the generator matrix. The rows of the generator matrix describe the space of code words. The rows of the parity check matrix describe the space being orthogonal to our valid code words. So any valid code word I multiply with H transpose will turn out to be 0. So if I have here a valid code word, any of them AI, it contains our bits U0, U1, U2, U3. So we have 4 information bits in our 7,4 Hamming code. We have 3 parity bits. And 4 bits. Parity bits. And if we multiply those let me write this underneath each other. So we get U0 times 1 plus U1 times 1 plus U2 times 1 plus P1. And we know our valid code words are orthogonal to H transpose. This is why we know that this sum turns out to be 0. So the modulo 2 sum over these 4 bits must be 0 if, the sequence that we multiply with H transpose is a valid code. Okay, and here we basically get the same. We get U1 plus U2 plus U3 plus P. We had P0 here and here P1. Always be careful if you start counting at 0 or at 1. And sometimes also mix this up. And for the last one, we get U0 plus U1 plus U3 plus P2 must be 0. So actually our code can be also completely described by this matrix H transpose, or the other way around. We can also say, we can also use H transpose or H to encode our sequence. Because if you look at this now here, we get U0 plus U1 plus U2 plus P0 is 0. I could subtract P0 now, bring it to the other side. But as we are in the modulo 2 space, this also means U0 plus U1 plus U2 is equal to P0. So basically, what I want to say is that also the parity check matrix can be used for encoding. So we have the information here how to get our parity bits. So for the second one, we would get U1 plus U2 plus U3 will be equal to P1. And from the last one, we get U0 plus U1 plus U3 is equal to P2. So also the parity check matrix can be used for encoding the generator matrix. The generator matrix is actually not even needed. As we will see later on, in 5G systems, it's actually done this way. So there are just the parity check matrices defined, and they are also used for the encoding because the parity check matrix contains the information how to calculate our parity bits. So in 5G, in the 5G standard, only parity check matrices are defined. And we will see they also have the structure being a bit more difficult. As here in our example, for example, they will not have the identity matrix down here, which means it actually will not be easy to get from the parity check matrix to the generator matrix. So for codes in practical systems, the parity check matrix is a bit more difficult, which means the step to come up with the generator matrix will be more difficult. And this is why in this case is actually the parity check matrix is directly used also for the encoding. This just as remark here. I will come back to this when we actually see how one of these generator matrices in 5G systems looks like. But here it's important for you to understand if we multiply something with the parity check matrix transpose and the result is 0, then we have a valid code word. And this is actually what is used now in this Tenor graph to illustrate. Let me go back. Here you basically can identify these check nodes and all bits contributing to this check node. So this first check node, basically we get it by U0 plus U1 plus U2 plus P1. So here we get the modulo 2 sum of these 4 guys. For the second check node, we get this blue bits contributing to the modulo 2 sum and so on. So this Tenor graph is just an illustration of these equations here. So what is going on when we multiply with this parity check matrix? Okay, so is this clear what the parity check matrix and the Tenor graph have to do with each other? The Tenor graph is basically just a graphic representation of the parity check matrix. Okay. And we can use the parity check matrix once for encoding and also for decoding, as we use it typically to calculate the syndromes. And with the syndrome, we can basically work further, as we will see today. Okay, but before we do this, we also come to some properties of this LDPC codes. Some properties. As I said, they are typically defined by their parity check matrix. And I come up with an example here. So we have let's use one like this, 1, 1, 1, 0, 1, 0, 0. So let's use one which has an identity matrix here at the end and at the front. It's actually the one from the Hamming code. Use this one again. So we have some definitions here for this parity check codes. We can define so-called row weights. WR. So we have a row weight telling us how many bits are different from 0. So we have here 4 bits being different, here also 4, and here also 4. And we also can have column weights. Very easy, just counting the bits different from 0. WC. This will be here 2 bits different. 3, 2, 2, 1, 1, 1. Just to introduce some definitions. And then we said actually this LDPC codes will work really well if we have large matrices with only few ones. So typical LDPC codes. Use sparse matrices. So this means the column weights WC is a lot smaller as the number of rows. And WR, so the row weight, is a lot smaller than the number of columns. And of course, it's a good question to ask here why. We will see later. We need to go a bit more into details there.
Professor?
Yes.
This row weight is like it is number of bits which are non-zero, right?
Yes, yes.
And for non-binary codes also, is it holds same?
Yes, so for the non-binary codes, it will be a bit more difficult. So of course, let me see. So once I was dealing with a non-binary code, and there actually it was distinguished. Of course, you can also define a matrix describing how many entries are different from 0. But if it is important, if the entry is a 1, a 2, or a 3, it might be also useful to distinguish between the several non-binary values. There it depends a bit on what you want to do with this matrix. But in general, the definition when we talk about the LDPC codes is really talking about non-zero elements. So we will also get to know non-binary matrices when we come to the definition of this LDPC code for the 5G systems. And there we talk about sparse matrices if we have few non-zero elements. So there we will have also elements being different from 1. But this sparse property is just related to the non-zero elements. Okay, so let's see how we continue here. Yes, so we have some more properties. So we can have regular or irregular LDPC codes. Regular versus irregular. And here I also brought some examples. So for this regular property, it's defined by the row weights and the column weights. Let's start on the right here with the regular. So we talk about a regular LDPC code if WC is constant, so the column weight for each column W row must be constant for each row. And there must be a relationship. The row weight needs to be WC, so the column weight, times n over n minus k. So let's come up with an example. e.g., if we have like a 8,4 code. So this means n, the code word length is 8. We have 4 information bits. So this means WR must be WC times 8 divided by 4. So in this case, it must be WC times 2 if we have an 8,4 code. And I actually provided you a matrix to fulfill this. Matrix H. We have one here, starting with a 0, 1, 0, 1, 0, 0, 1. So actually this example on the lecture slide is not really correct. You see we only have 7 columns here. So we would need one more column. Yes, so let me see. So this needs to be like this. So here we have a WR being 4. We need next row 1, 1, 1, 0, 1. Just coming up with an arbitrary example. So we have 4 ones here. So let's do it like this. We have 4 here. Next one 0, 0, 1, 0, 1, 1, 1. 0, here 4, and 1, 0, 0, 1, 0, 1, 0, and here also 1 is missing in the lecture slide. And we have WCs being 2, 2, and you see for each of the columns we have the weight 2. So this would be a regular or a parity check matrix for regular LDPC code. And the major benefit of this efficient encoding possible. So this has some advantages when it comes to the encoding, and always imagine larger matrices here. For example, in satellite TV, they use here matrices of having like 10,000 rows and 20,000 columns. So really huge matrices where efficiency sometimes is really a point. It's important. And on the other hand, we have the irregular codes. LDPC code. Well, those are the other ones who don't fulfill this constraint. The ones which don't fulfill the conditions. On the right. For example, the one we used, our Hamming code, it has different column weights. So this is not a matrix for a regular LDPC code. And here I also have some additional remarks. For example, powerful codes. Codes have been found by computer search. E.g. by using random parity check matrices. Okay, so there are different methods how to design this kind of LDPC codes. We can use this more like structured methods, or we can use like random parity check matrices, where we will see later on what could be or what is beneficial in such a kind of parity check matrix, or what is bad in this kind of parity check matrix. For example, we will see that if we can observe, we will talk about this later. So we will see actually some structures in this parity check matrices which are bad for the performance, bad for the decoding. And yes, this is also why these structured matrices sometimes have the drawbacks, as they basically show this pattern which are bad for the performance, whereas this completely random parity check matrices, yes, at least don't have this structured type of problem. Okay, but we will see this when we talk about the matrices used in 5G. So far, just remember this property. We can have regular LDPC codes, we can have irregular ones, whereas the regular ones have the benefit that they are efficient to encode. Okay, so let's see how to continue. Yes, so actually, I would like to skip this. So on the lecture slides, I have now one describing how to get from the parity check matrix to G. But typically, as I already explained, in 5G systems, we don't actually work with the generator matrix G. We do both the encoding and the decoding just based on the parity check matrix. So here we have a question: does this mean techniques like machine learning could be used to find the optimal age? Yes, actually this would be a good approach. And yes, machine learning algorithms could be applied to improve a parity check matrix age. This is true. But we will see, we also can introduce some site constraints later on to get a better matrix age. Just a very good hint. Then on the lecture slides, so let me show you this. I introduced here the parity check matrix that was actually used by Gallagher in the 60s when he came up with this kind of LDPC codes. And notice this also has a certain structure. It's not really a huge matrix, but for the 60s, this was basically his idea how to get started with this kind of decoding schemes. And I think we can come back to this one if we know a little bit more about the decoding procedure. So, but just to show you one typical LDPC codes, the one which Gallagher started with in the 60s. Okay. So let's come back.
Sir, I have a question.
Yes.
This formula which you told for regular LDPC code, will that work for irregular LDPC code as well? This formula WR is equal to WC into N divided by N minus K. This is a standard formula.
Yes, this is like a standard formula. It comes from the definition of regular LDPC codes.
It won't work in irregular LDPC code.
No, just look at the one that we have before. Let's look at this one here. Notice we have here a column weight of 2, here a column weight of 3. So this means the column weights are not identical. So this is already why it's not a regular LDPC code. And also, well, then of course also not the relationship that the row weight must be, a certain factor times the column weight will also not be true. So here it's already violated because we have different column weights. For the regular one, we need to have equal column weights. Okay. Okay, so let's approach the decoding. So first, explained simple, because we will see later on it will be in practice more difficult. First, explained simple. using, we use again the 7,4 Hamming code. And we use a binary symmetric erasure channel and a binary symmetric erasure channel. And maybe let me briefly explain again this binary symmetric erasure channel. So we have here zeros and ones that we would like to transmit. Mapping to plus minus square root EC. So for example, for simplicity, we use again EC being equal to 1, so to map to plus minus 1. So you could imagine we transmit either here plus minus 1. We will actually use later on a mapping where we map the 0 to plus 1, the 0 bit, and the 1 bit to minus 1. So this would be the corresponding sequence to be transmitted. And now we just want to imagine a channel model here, which will result in this binary symmetric erasure channel. But we could also model this as adding some noise here. For example, AWGN channel. Which would result then in a kind of noisy signal. And we would simply, in order to model this kind of binary symmetric erasure channel, simply introduce some levels here. Let's make red. And we would need some sampling points. So let's say we do a very basic scheme. We just sample in the middle of the bit duration. It would not be very smart to do it this way. Sample this one here, sample this one. Maybe let's draw the second one. It depends a bit how you have drawn it. So let's assume this one got correctly. Not to introduce too many mistakes. And we would model this basically as 3 outputs. So if we observe values larger than this upper threshold, we say it's very likely to be a 0 bit, very likely. If we observe values smaller than this lower boundary, we say it's a 1 bit, very likely. And if we observe a value in between, we say, well, it could have been a 0 or it could have been a 1. So we are not safe about our decision. So we just call this X, the erasure symbol. /unsafe decision. So this is just to give you an understanding where now our samples come from. Yes, so here's the question, are we using threshold detection mechanism here? Yes, we could really do simple thresholding. So if you imagine here just voltages at the receiver, maybe at the output of a low noise amplifier, you could simply measure voltages, sample the signal, and look, is your sample larger than, let's say, 0.2 volts? Then you say we are safe. If it's between 0.2 and minus 0.2, you would say, yeah, it's unsafe, I'm not safe about the decision. And if it's smaller, you say, okay, then we are safe. On the other side, it's very likely a 1 bit. So that's the most simple method of detection which will provide you some information on the reliability of your observation. So just note, if we would model a binary symmetric channel having only outputs 0 and 1, it would correspond to a thresholding around 0. Then we can only say, well, if it's larger, it's a 0. If it's smaller, it's a 1. But we have no idea how safe our decision is. So if we just decide around 0 and I have a value of 0.01, it's almost equally probable that this was a 0 or 1. And this information is completely lost if I do this hard decision detection. And here that's the next better level, coming up with a boundary, with a region where we say, here we are not safe about the detection. And we try to use our coding scheme to basically get some more information then on these unsafe detected values here. So we will use the information that we can extract from the parity bit, from the links, how the bits are linked together to the syndrome, to the check bits. We will extract their information now on this unsafe detected bits X and see if we come up at the end with a more reliable estimate on this unsafe bits. So here we have another question. Is it similar to PCM, so the pulse code modulation? Yes, well, it's of course similar. It is some sampling, but here just take it as illustration. In practical systems, you would not apply a sampling in the bit middle. So you know the more smart methods from Mike Wolf's lecture, you would do some matched filter decoding, some correlation decoding, and some sampling after the correlation. So just take this here for illustration. For understanding, it's okay. We have sample values that could be safe, and we have sampling values that are unsafe. And we try to get some more information on these unsafe ones by using our coding scheme. Okay, so let's see how this works now. Coming up with the Tanner diagram again for our 7,4 Hamming code. So we have actually a syndrome of length 3. So this means we get 3 check bits. We have code words of length 7. So this means we get 7 bit nodes here. 5, 6, 7. We already explained how the bits are linked together. The links here. So the first 3 contribute to the first check bit and the first parity bit. For the second one, we have the second one contributing to this one, third one, and the fourth one, and the second parity bit. And for the last one, we basically have the first, the second, first, the second, and the fourth. Well, and the last parity bit. So contributing to this, guys. And now basically the input of this Tanner diagram will now be our received sequence. So assume we receive Y. So we have some safely detected ones and we have some unsafe ones. And let's use the ones from the lecture slide. So I say the first one is detected safely. The second one, we are not sure. Third one, a 0. Fourth one, a 1. Another one, and 2 more where we have an unsafe detection. So those are the difficult ones. So, and the question is, can we use our relationships here from our coding scheme to actually decode these unsafe detected values correctly? Unsafe detected values. Yes. So we want now to exploit structure of this parity check matrix, exploit this Tanner graph, and see if this helps us to safely decode these values. So if you look at this first check node, we see what comes together here is the 1 plus x plus 0 plus 1. At the second one, what comes together is x plus 0 plus 1 plus x. It's not writing. It's not a minus, it's a plus. It won't let me write it. Okay, so here we have this sum, and at the last one we have 1 plus x plus the one from here plus the x from here. And we know in order for y to be a valid code word, these check nodes, which actually correspond to the syndrome bits, must be 0. In order for y to be a valid code word, the check nodes must be 0. Yes, and there you actually see that we can use this kind of information to actually decode already this first guy. As we see here. This means this check bit can only be 0 if this unsafe detected bit is a 0 as well, because then we would get 1 plus 1, which is 0, plus 0, plus 0. So X is probably and you can imagine how this works. We will feed now this additional information back to our bit nodes. I think we don't need an additional drawing for this. You can also see this nicely on the lecture slides. So we get a 1 here.
Professor,
Yes.
is X is 1 or X is 0 here?
Oh, X must be a 0, of course. Yes, yes, you are right. Because if it was 1, the sum would be 1, no? Which is bad. Sum needs to be 0. Yes. So, and we would use this to feed back and then we would actually get also the 0 here. Yes, and here's already the question. What about the second one? In the second case, we cannot tell. So we have 2 unsafe. So you see there are a couple of combinations. So the first one could be a 1, the last one could be a 0. Then the sum will be 0. Or the first one can be a 0 and the last one 1. So here we have no unique solution for this case. We can find this in another iteration. So if we solve first for this one, feed back to the bit nodes, and then next iteration, feed forward to the check nodes, we know that the first X is a 0 bit because we know it from the first check node. And then we have only one unknown, then this one must be the 1 bit. Then we know these 2 guys, feed them back again to the bit nodes. So then we would know also this guy. And the same for the third check node, which would give us the last unknown. So here we already see that some kind of iterative decoding will be required. We need to send back and forth information between the bit nodes and the check nodes. In our example, very simple information, just this erasure symbols that we modeled here. This is how we describe the uncertainty in this very easy description. We will see later on in the practical systems, it will be done slightly differently. So there, what is passed back and forth will be just probabilities. So if the bit value is here more likely to be a 0 or 1, maybe with 90% probability, we observe a 1 here, and how to deal with this information here on the check nodes. So this will be the more difficult part to explain. But for the basic principle, how we can benefit from iterating in this Tenor diagram, this can be shown by this very simple example. So maybe let me also show you this example completely on the lecture slides, that we don't have to draw this Tenor diagram like 10 times. Yes, so here you basically see this first iteration. So we found out the first unsafe bit. We feed this back to our bit nodes. Then we know this unsafe bit was a 0. We have another iteration. We feed forward again our bit nodes, which makes here only one unsafe bit remain. So this means now we can basically decode these two missing ones. The red one here must be a 1 to make this 0, and this purple one must be a 0 to make this sum here 0. So with this we can decode the message completely. And I actually introduced one last iteration. If we decoded this once, feed forward again, we will see the sum here at the check node turns out to be 0. So this means our decoding result will be this one, and you could verify it by multiplying with H transpose. Of course, this is a valid code word. Multiplying with H transpose is actually the same as saying we calculate here the check nodes, because this is exactly the graphical representation of this parity check matrix. Okay, so here's one more question related to the erasure symbol. So let me get this here away. Just so here's the meaning, the question, what's the meaning of this erasure symbol? So this is basically the most simple channel model that we use in order to process some kind of reliability information of our detections. So if we decide just around 0 with the hard decision detection, we only have values which can be 0 or 1. So introducing this model already gives us some more information on the detection. We get some reliability information. We know our value is pretty safely in the range where we expect it if a 0 bit was transmitted, or in the range that we expect if a 1 bit was transmitted. If we observe values in between, like here around 0, we would say, well, here we are not really safe about the detection. This could have been, look at this example, this could have been either a 1 bit or it could have been a 0 bit. We are just not safe. And we denote this by this so-called erasure symbol X. So looking at our received sequence, I have some safely detected bits, and I have some bits where I'm not safe about the detection because the values were somehow in between the two values that I would expect. So the most simple model representing some reliability information. And we will extend this further by not using any hard detected values, but working here with probabilities instead. This will be the next step. This is just the most simple model that can be used to explain how the processing in this Tanner diagram will work. Okay, are there more questions related to this one?
Professor?
Yes.
I have a question here. Like using this decoding, we are sure that whatever we decoded, it is a valid code word. But
Yes.
are we sure that whatever we sent, that is the only one we receive? Because if we sent one code word, which is corresponding to the 0 syndrome, then there might be some in 7,4, we are having, I think, 4 a valid code word corresponds to 0 syndrome, right?
Yes. So you already understood a lot. So of course, if we force the syndrome to 0 at the end, so we know, of course, then what we come up with is a valid code word. But what we don't know is if this is actually the code word that was transmitted. So there we cannot be really safe, because if we have too many errors, it could of course also be that our decoder comes up with the wrong estimate. So this means, of course, also after decoding, we could get errors. For example, if we, let me see. if we had even more unsafe detected bits here, then it is likely that our decoder will fail. Of course, it will come up with a sequence being a valid code word, but it could be a different code word as what we actually transmitted. So still, there's a certain probability of failure, just depending on the amount of information that we have available. So you see, if we would model more unsafe decided values here, the amount of information gets less and less and less. Or let's also consider the worst cases. That's always also good, thinking about worst cases. Worst case would be you detect values here, like being around 0 here, around 0 here, around 0 here, and here. So this means you hardly have any idea of what you detect there. Like having only unsafe detections, there's not really a lot you can do with it. Then also the best coding scheme would fail. So it depends on the amount of information that we actually have available from our detection. We have more or less reliable values, what we will describe later on by probabilities. But you are true, the detection could also, or the decoding procedure could also converge to a wrong code word. Okay, are there more questions? And here I have a slide, but there we want to continue with the new slide set. Let's look at this one. So we want to talk about the message passing decoding. So we actually want to see how this is done in 5G. We have some a priori information just from our detected values. In our case, this was the information safe detection or erasure symbol, unsafe detection. So we can also go a little bit deeper there, how to describe this information. And we will talk about the so-called a posteriori information or extrinsic information. So for example, explain this. What information about this bit, this second bit here, can be extracted from all the other bits? So you see the bits are linked somehow together over these check bits. So we can get some information on the second bit from knowing the other bits. So this is the so-called extrinsic information. So the information on bit 2 that we do not get from bit 2, but which we can extract from all other bits. And we have the intrinsic information. So this is the information on bit 2 that we know from observing bit 2. So we have two parts of information that we will have to deal with: the information from the observation of the bit and the information that we can extract from the other bits being linked together as described by the parity check matrix. So two parts of information that will appear later on if we go into more details. And then, of course, we have this passing back and forth information between the bit nodes and the check nodes, and thereby improving the estimate on our code word. Okay, and here I actually have also linked the webpage of Professor Gallagher. So I'm actually not sure if he's still teaching there. But you can check if this webpage is working. So there you find some of his publications and also the original publication. Okay, so this was just basically the introduction to show you how this parity check codes will work, how we will use the Tanner diagram to understand these iterations in this LDPC decoding. And next we will go some more into detail. Just have 15 minutes left, but we can already start here. So there I will show you this new lecture slide set, which is also available on the webpage. So I think I made this 1 year ago. Oh, why is this not disappearing here? Oh, no, it's disappearing. Okay, where I basically describe this LDPC codes a bit in more detail. So in order to understand this, we need a basic understanding of block codes that we have already. So we know what a parity check matrix does. We know what a syndrome is. We know the zero syndrome for valid code words. So this we should know. And we also will need some more understanding of this Gaussian distributed processes. We will need to talk about, we will use the additive white Gaussian noise channel model again, and therefore we need to know how to deal with these Gaussian distributions. And we will need to know something about probability theory, and we will get to know these log likelihood ratios. And here also the learning goals. We should know how LDPC codes work in practical systems actually, and how this decoder could be implemented. One specific one that we use here, the so-called sum product decoding. So of course, there's always research going on how these decoding schemes or how these codes could be decoded efficiently. But this is not so much part of our lecture. The goal of the lecture is to give you an understanding on the theory, so what is done there, what is important. The question of implementation and efficient implementation is a different one that we will not be able to answer. Okay. So some facts. I also repeated here the facts with some more updated information. So actually, there are, of course, also comparisons between LDPC codes and the turbo codes, which were used in 3G systems. So there I referenced the document. They come very close to the Shannon limit. So in Mike Wolf's part of the lecture, you actually derive the channel capacity. So how much information can be transmitted for a certain signal to noise ratio at a maximum without errors. And we can reach this channel capacity by using this kind of LDPC codes. They come very close to the Shannon limit. And they are used in satellite TV, we already know this. And in 5th generation wireless systems, this is the part that actually interests us most. So I have some more facts here. They are also standardized in IEEE 802.16, so in the WiMAX system and in the wireless LAN systems. So there also LDPC codes are used. Then also what we know already, they are just block codes with large parity check matrices. Yes, and of course, it's not a surprise. The complexity will, of course, increase if we increase basically the minimum Hamming distance of the code. So if we make the codes larger, the matrices larger, of course, also we will have an increased complexity. But here actually a linear increase with the block length. Whereas for other codes, for example, the convolutional codes or the turbo codes, there we often have like a exponential growth in complexity, or at least a square growth in complexity. So it's also good here that, well, the complexity increases just linearly with the block size. Yes, and the challenge is to find good parity check matrices. And there we will get an idea how this is done as we look at the 5G standard. Yes, and the difference so far to what we did, we treated the block codes and we got to know this syndrome table decoding. So the difference now is that these LDPC codes are decoded iteratively by using this like Tanner diagram. Well, and why? You can imagine if we have parity check matrices of size 10,000 by 20,000. So this means we have received sequences of length 10,000 bits. Just imagine you would have to come up with a syndrome table for code words with length being 10,000 bits. So this is not really practical, hard to implement. And also the maximum likelihood soft decision decoding, where you compare the received sequence with all possibly transmitted code words, like calculating the Euclidean distance to all of them, would not be really practical if we consider these large sets of code words. So there, this is just not practical. This is why there we need different methods to decode it, and there this iterative decoding methods come into play. And I also did some research on the efficiency. So of course, one question is also how the complexity turns out to be, how is the energy efficiency? And there I found a publication by Nokia and Alcatel-Lucent comparing the complexity between LDPC codes, polar codes, and turbo codes. So the turbo codes being used in 3G systems or 4G systems. We have here a so-called silicon area efficiency. So you can implement like chips producing throughputs of like 5 gigabit per second on 1 square millimeter. And there, if you use the LDPC codes, you can already implement like 10 gigabits per second on 1 square millimeter chip size, basically. So when it comes to implementation efficiency, obviously the LDPC codes outperform the polar codes and also the turbo codes. So we get higher throughputs for less chip size. Looking on the energy efficiency, so there one way to describe this is describing how many nanojoules are used to decode the bits. And there we can actually decode like 100 bits with 1 nanojoule energy. Actually more than 100 bits per nanojoule. For the polar codes, we are below 100 bits per nanojoule. And for the turbo codes, you see they need quite some more energy for the decoding. We can only decode, let's say less than 1 bit with 1 nanojoule energy. So when it comes to efficiency, implementation efficiency, energy efficiency, the LDPC codes are really excellent. And this is actually why the turbo codes from 4G standards have been replaced by LDPC codes and also polar codes for the 5G standard. So these are very interesting figures. So sometimes when we talk about theory, we completely forget about implementation issues. But here you actually get an idea what the main reason was to switch from the turbo codes to LDPC codes. And I think it's also should be also linked here. But you can also find this if you search for an item. Okay. Then the basic principle. I also tried to explain this already. Let's say we are interested here in the 3rd bit. And now the question is, how do we get information on this 3rd bit? Of course, we get information from the observation, so from the sampling value of the 3rd bit, but we will also get information from all other bits. Because also all the bits are somehow linked together in this parity bits. So this means we can extract information from the observation of the other bits and the way they are linked together in the parity bits. This can be used to update, to improve the information on our bit of interest. As we have seen before in this simple example with the Tennant diagram. So, let's see. And this is actually where we want to continue. We need some more theory to understand how things are done in 5G systems, in practical systems in general. So we do not do more introduction here for the LDPC codes. Now we get back to theory. So how is it done? Is the decoding in practical systems? Soft values are used. Remember, right at the beginning, we derived some stuff where we saw that, of course, when we process soft values, we get a performance gain as compared to the hard decision processing. Soft values are used, e.g. Channel outputs or received values from an AWGN channel. So there we can have any real valued sample value that we observe here at the output of this channel model. So it can be 0.7, 2.7, depending on the received energy, any value. But we will actually not work with these values. We will work for the decoding. Probabilities. So for example, what is the probability that received value e.g. let's say here x being 0.2 was +1 at the transmitter. Oh, actually, I called the received values y, so we should call this here y, sorry. And often not just these probabilities are used, but ratios between probabilities. The probabilities are typically used in ratios, and we will get to know the so-called log likelihood ratio. So it's the logarithmic ratio between the probability if the bit is more like a 1 or more like a 0. Or the mapped one more like a +1 or more like a -1. Log likelihood. Abbreviated as LLR. So actually what is passed back and forth in this Tanner diagram is typically this LLR information, this log likelihood ratio. So the probability, if the value that we are observing there is more likely to be a +1 or more likely to be a -1. And of course, this we will describe by some formulas. There we need, again, some math dealing with this Gaussian distributions, but we will actually see this in the lecture in the new year. So in the next lecture, we want to continue here. And yes, so that's it basically for today. Do you have questions so far? Yes, so there's a question. In the Moodle, there were a few past year papers for reference, but now it's not there. So I know I uploaded one, but I will check again the Moodle webpage for the updated papers. Maybe Mike Wolf took some out of the previous exams. But well, for my part, so there are just not so many previous exams where I asked questions for the LDPC codes. Because it's quite new that I treat it in that level of detail as we will do it in this semester. So there will be a kind of new task. So you have not seen a task related to this. Well, but I will give you some hints in the next lectures what could be asked if we talk about the LDPC codes. Yes, here's a question, how the LLR from the bit error ratios which we saw previously. So of course, this is a question going a bit towards the future, but let me show you quickly on the slides so you will see there are quite many slides. It's like 85 pages, but I have here actually a working example where I calculate on this. Let me show you the one I'm interested in now. I think it was this one, yes. So here, just look at this table. I made a model where I want to transmit these bit values, 1, 1, 0, 1, and so on. I map this to ± square root EC, assuming EC is 1, just for simplicity. So mapping the 1 bit to -1, the 0 bit to +1, those are the values that I transmit over my additive white Gaussian noise channel. So some noise is just added. So at the receiver, I observe these noisy values, being more or less similar to what I actually transmitted. So notice I transmitted a -1, I observe a -0.8, and here I actually calculated the probabilities. For a certain signal to noise ratio, of course, I must have assumed. So if I observe a -0.8, then with 99.7% probability, this was a +1 bit or a -1 value that was transmitted. It could also have been with probability like 0.3%. It could have been also a 0 bit. And the noise was so large that we actually end up with a -0.8. So if I transmit a value +1, my noise is -1.8. I will also observe a -0.8, but it's way more unlikely. So we can come up with these two probabilities if the bit is more like a +1 or more like a -1. And the log likelihood ratio actually describes the log of the ratio of these two probabilities. So it's just a measure. How much is this received value looking like a -1, or how much is it looking like a +1? So you see, if it's very safe to be a -1, we get a large negative log likelihood ratio. If we have values being pretty safe to be a +1, we will get a large log likelihood ratio, a high probability that the bit was a +1. And we have the more unsafe detections. So let's take the last one here. We transmit a -1, we observe a +0.2. So actually, if we did just a hard decision detection, this one would go wrong. We see a value larger than 0. We decide for a +1, which would be wrong. Looking at the log likelihood ratios and the probabilities, with probability 80%, this would be a +1. With probability 20%, this would be a -1. So here also the probabilities indicate that it was more likely to be a +1. But we also see a fairly small value on the log likelihood ratio. So if we observe log likelihood ratios around 0, means we have a very unreliable observation. If we observe large log likelihood ratios, we have very safe detections. And the information on the transmitted value is actually contained in the sign of the log likelihood ratio. And then we will actually see in the decoding procedure how these log likelihood ratios will evolve when being passed back and forth in the Tanner diagram. So actually, we have so many slides because here I made a working example where we actually should see, yes, how this log likelihood ratio evolves if we pass back and forth. So these numbers, these likelihood ratios get bigger and bigger. Our estimate gets more and more reliable. So this is actually the goal of this whole iterative decoding, improving the iteration, the information from iteration to iteration. Yes, but your question already went a bit into future. But I think you already got now the idea on the meaning of this log likelihood ratio. Okay, are there more questions? Okay, so then I think we are done for today. Thank you again for your attention. And it's the last lecture for this year. So I wish you all the best for Christmas time, New Year's Eve. And yeah, try to relax a bit. Don't only study, try to get some fresh air, visit the nice Thuringian forest, and yes, enjoy also your free time and stay healthy. Okay, so have a good time and see you again next year. Goodbye.
Bye, sir. Happy New Year.
Yeah, thank you.